So the chain rule can help us find the derivative of e raised to a multiple of x or t power. So before, when we've looked at derivatives involving e to the x, it always wound up being the same as the original function. That's because we didn't have a coefficient on the variable, but now we have a coefficient on the variable, so let's see what that does. So if we apply the chain rule, with the outside function being a power function, u to the a, in this case my coefficient's a, that's my power, and my inside function's e to the t, then the derivative of my outside function, I bring down the exponent, that's a, u, and then I subtract from the power, and then the derivative of the inside function, e to the t, is just e to the t. So look what happens when we put all this in the chain rule. When I evaluate that outside function at e to the t, and then I multiply them by e to the t again, I end up with the same coefficient in the power and the same coefficient from the power rule down here multiplying e. So it's similar to the power rule when you have when you find the derivative of e to the at, in that you bring down that coefficient, but you don't subtract 1 from the power. Here's an example of e to the 3t. So you can go through it with the chain rule, and the final result is going to be the coefficient of t is 3, that's the coefficient I've brought down, times e to the 3t again. Here's another example with a negative coefficient. We still get the same thing. We're still going to have the coefficient of e to the e term as the original coefficient in the power, which is -4. And then the coefficient of t in the exponent is also -4. So one thing you can kind of generalize when you use the chain rule and the outside function's a power function. So notice that the derivative is always going to be of this form, where you've brought the power down and you've subtracted 1 from the original power for the outside function. So you can use the chain rule with other rules, not just the power rule. So you'll be using with the product rule and the quotient rule. So let's look at this guy. So we're going to be using the quotient rule and the power rule here with the chain rule. So the outside function is going to be u to the 8th power, that's a power function, and the inside function is this rational function. So the derivative of the outside function is just 8 times u to the 7th, and then we'll need to use the quotient rule on the derivative of the inside function. So the derivative of the numerator is 3x squared times the denominator minus the numerator times the derivative of the denominator, all over the denominator squared. So now I need to use the chain rule. So here's the derivative of the inside, simplified. And here is that derivative of that power function evaluated at the inside function. And here it's multiplied through. So now let's look at an example of the product rule and chain rule. E to the at times sine of bt. So applying the product rule, the derivative of the first factor times the second plus the first factor times the derivative of the second. And we saw that the derivative of e to the at is just a e to the at. And the derivative of sine of bt is just b times cosine bt. So this is the derivative of the inside times the derivative of the outside. And then putting those into the product rule, this is what we get. And notice that if we got higher order derivatives, if we kept differentiating this, a pattern would emerge, because the b's, you'd alternate between sine and cosine for the derivative, and then you would just be getting higher powers of b and higher powers of a. So the chain rule also allows us to now say what the derivative of an exponential function is with a base besides e. And it all boils down to the fact that this is one of those rules of exponents from algebra. So I can express b to the x as e to the ln of b raised to the x. So now I can look at this, which is the same as e to the x raised to the ln of b. So now I can look at this as a composite function. My outside function is u raised to the ln of b, and my inside function's e to the x. So this is just a power function with the power equal to ln of b. Remember, that's a constant. So it's like n is equal to ln of b. So I can apply the chain rule. So f prime of u is, bring down the power, ln of b, times u raised to the ln of b minus 1. And then I need to find the derivative of the inside, which is just e to the x. And now applying the power rule, I get the ln of b times e to the x raised to the ln of b minus 1, which is the derivative of the outside function evaluated at the inside function, times the derivative of the inside function. And then when I multiply through this e to the minus x and e to the x, I'm going to get ln of b times e to the x ln of b. So I'm just left with x multiplied by ln of b, the minus x and the x multiplied to 1. So now I have a coefficient of ln of b, and I can switch the order of these factors in the exponent. So I have ln of b times e to the ln of b raised to the x power. But e to the ln of b is just b. So I'll go through all that. And the final result is the derivative of b to the x is just b to the x again to b. 10 raised to the 2t power, I can re-express that as 100 raised to the t power. So the derivative is just ln of 100 times 100 to the t. That's it. Simple. It's just remembering that ln of b times b to the t formula.